Covariant vectors. Here we're going to differentiate between covariant and contravariant vectors by using the placement of the subscripts or the superscripts. So here with a subscript, that's going to mean a covariant vector, and the superscript is going to be referring to a contravariant vector. Now let's just review carefully the contravariant vectors. The transformations would be given by these set of equations here, where the prime framed you see slanting in the upper right and the unprime in the lower right, and you have the prime on the left, the unprime on the right, and the partial derivatives with the prime on top and the unprime down below, with the sum on the j. Now when you look at the definition of a covariant vector, we're going to see that the slant that I have here indicates that the prime is on the bottom instead of on the top. So the top slant here is your JJ, and your bottom slant here is your II with the primes. Remember, I is not summed on because there's one I on the left and one I on the right. However, the J is summed on 1, 2, 3 because you have two J's on the right hand side. Well, the transformation for these can be written in any order. Since this is a simple multiplication, you can put the AJ on the right or the AJ on the left. Well, the differentials transform in the contravariant manner, as we have seen in the previous class. We look at dx prime I, where I is 1, 2, or 3, and that's simply the derivative of the new component here, the I component with the prime, with respect to 1 and with respect to 2 and the 3 variables. And then in summation convention, we simply write the one term down where it's understood, you sum over the j's. So here's a nice little review of the definitions, which we're going to investigate with covariant vectors in a second. But just think of the primes on top here and the primes here slanting toward the bottom, slanting toward the top on the left and slanting toward the bottom. Now, example of the covariant vector transformation is going to be one involving the gradient. So if we set up the gradient is simply a operation you can think of where you have a function f, and when you take the gradient you wind up with a vector. So f is a scalar function, and if you take the gradient, you get a vector by taking the partial of f with respect to x, then slap on the I hat, partial of f with respect to y, slap on the j hat, and with z, for the third case here, this is simply showing you the change of the function along the x, y, and z directions. So if you have the some rotated coordinate system or some other system, if it's rotated, then you have new I, j, and k since you have rotated them, and the function then can be expressed in terms of the primes, x prime, y prime, and z prime, and you would do the same thing. But now watch when you do the laws of partial derivatives to relate one to the other. See, these are your components in one frame, and here these are your components in the other frame. So if we look at the partial of f with respect to x prime, we can think of that as the partial of f with respect to x, and then the partial of x with respect to x prime, and then the partial of f with respect to y, and the partial of y with respect to x prime, and so on. So when you set it up this way, you can immediately see that the prime now is going to slant, see, downward. See, the new coordinates, this is a new coordinate in the new frame of reference. I say component, that's basically called a component, since the coordinates will be the x, y, and z, and the x prime, y prime, z prime. So the new component, the new vector component, a prime sub I, is really given here by the partial of f with respect to the coordinate x prime, all right, x prime here. And if you look here at the old one, you simply had f and x without the prime. And if we look at how we're relating this new one, this is the first one here. See, the first one. And that first one, where I is equal to 1, notice that over here you have then the old ones. This would be the old first one, the old second one, the old third one, because x is the first coordinate, y is second, and z is the third. So you can see that you're basically setting up your partial derivatives here, where you're taking the derivative of the x, y, and z up top, but down below it's still the prime. See, so here that's why the prime down here, which is fixed, this is x, 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 that's the first coordinate, where you have here I is equal to 1, and then the j then does the sum, which should be, this would be here the partial of f with respect to x. This is a 1, this is a2 and a3. See? And that's our prototype to understand the covariant transformation. So let's get some practice here with looking at polar coordinates. And here, first, let's see, we'll go with the polar coordinates, simply reduce, you can think of reducing your spherical coordinates down to 2 dimensions, where you just have, say, x and y. So here we have the spherical coordinate system, where you have the r, the radius, we have then the angle theta, and we have the angle phi here. And this is like a door that's opening. This is r sine of theta up top, r sine of theta. Then when you hit this with the cosine of phi and the sine of phi, you get your x and you get your y. Your height here is your r times the cosine of theta. And if we want to look at the plane itself, x and y, where we just have the phi angle, this would be polar coordinates. We have no height here. We just have the I and the j hat. These are your unit vectors in the x and y direction, and we have rotated them here slightly to show you the angle phi. And this would be the angle r and the angle phi. So you can think of it as kind of like rotating the I and the j by a certain angle to get the other language, because this other language basically is looking along the radius as one unit vector, and then a perpendicular to that is your angle. You're sweeping along the angle. If you increase the angle, you're going to be heading in this direction. So the equations here are very, very familiar with polar coordinates. Your x is going to be your r, your radius times the cosine of phi, and y is r times the sine of phi. What about the unit vectors? Well, the unit vector here, if you went cosine of phi along the I direction and then sine of phi along the y direction, you would have your unit vector r. For the phi unit vector here, I like to think of it as going up with the cosine of phi. See, that would be this part here, cosine of phi times j hat going up. And then here going to the left with your sine of phi times in this case it's times 1 because there's some unit vector. So that's the minus sine of phi times 1 gives you your magnitude in the, let's say going here negative to the left, and that's the I hat to the left there, a negative I hat. So that's neat. And then you can simply solve for the I and the j hat in terms of the r's and the phi hat. That's not hard to do. A neat trick is to hit this one here with cosine of phi, and with this one with the negative sine of phi. Then when you add them, cosine squared and sine squared give you 1, and here you have a cancellation because here you had a cosine times a sine, and here you had a negative sign come in here, and negative sine times a cosine. So it's neat to work that out. And then you get simply here you hit this with the cosine, so it's cosine with the r hat. You hit this with negative sine, so negative sine phi hat, and there's your transformation. And similarly here, if you want to get j hat, then you hit this with sine and hit this one with cosine. So when these are squared and they add, you get the j hat by itself. So hit this with the sine, that's a sine with the r hat. Hit this with the cosine, it's cosine with the phi hat. That's neat. And then here you have a little homework problem. I'd like you to just work out some of these partial derivatives. Do this in detail, work this out, get a little workout, and get a good feel for how these derivatives work. So have some fun with that. And that essentially is a derivation of the gradient in polar coordinates. That's pretty cool. So I hope you enjoy the homework assignment and this lesson. And in passing, I also will note that you have done the gradient in cylindrical coordinates, because when you promote the 3 dimensions, polar coordinates, in the cylindrical fashion, you simply add in the height with k hat. See, so the partial with respect to z, k hat gets you cylindrical coordinates. Later we'll look at spherical coordinates.